So now we'll hear more about transactional experience domain. I will also personally be interested to hear about that. And just a couple of words about Giedrius. He's our staff engineer in transactional experience domain. I personally have not worked much with him, but I've been in at least a few situations where if you challenge something and people just answer, Giedrius said so, no one challenges again. So there's quite a lot reliability in the talk.
Yeah. Okay, thank you for the introduction. Yeah, so that's the thing with transactional experience. Nobody knows what we do. We don't know what we do. No, actually we do. So first things first, to know what we do, we split the member journey between making a purchase decision and the post-transaction. And we split it into 4 different stages. We call them the pillars of transactional experience. So there are a lot of things here. And there are a lot of things that are not written here. There are a lot of unhappy paths. So I've tried to basically take out the most happy path there could be. So we can take a look at the making a purchase decision phase. So we have teams that are basically working on price offers and creating the initial transaction. We have pre-order phase. So basically this is the checkout experience, shipping experience in the checkout. I mean, put-up point selection, label, estimation, and so on. So basically, we are creating the preliminary shipments there. We are updating the ledgers for transaction participants, and we are, well, most obviously processing the payment. And same goes for post-order. Whenever we process the payment, that's the point where we transition to post-order. So if the payment is successful, we then can use our preliminary shipment to get the actual shipping label, to start shipment orchestration, to communicate with Vinted Go or shipping services, and basically show the tracking information, perform auto actions, initiate reminders, orchestrate the feedback loop, complaints, and so on and so on. And basically, once this completes, this completes when we release the escrow amount to the seller. So this is an interesting concept because when the user buys an item, the money is not exactly immediately transferred to the seller. Rather, it gets transferred to an escrow wallet, that we call it like that. So the seller is not able to actually use that money until the buyer confirms that everything is OK. And once that is done, we say that we release the escrow amount, and we go into post-transaction phase. And in post-transaction phase, we issue invoices, we collect member feedback about the transaction, about the experience, about Vinted in general, and we perform payout orchestration through payment services as well. So if you look into this, you might see that we do just a bunch of orchestration. We have shipping domain. We actually have shipping business unit that's called Vinted Go. We have payments domain that actually do the integrations with PSPs and different providers. And we are just in the middle of this. So we are doing the orchestration between a bunch of different services. So to simplify, as it was mentioned previously, we are working on DDD. So this is a very simple and very crude context map of our domain. So now everybody knows what we are doing. So in the middle, you can see we have transactions. So the transaction is the entity that gets created at the start. So basically, whenever the buyer first contacts seller, and it gets deleted. It actually isn't deleted, but it should be deleted at the very, very last stage. And then it connects with shipping integration, with payments integration. We have balances, user wallets, we have conversations, we have billing, invoices, billing addresses, taxes, and then also feedback block. So obviously in the real world, we have many, many more stuff here. We have a lot of unhappy paths, a lot of administration tooling that's also part of those contexts, but I just wanted to make it a bit simpler. So I would say that these represent the pillars of our experience. So yeah, all good things start from a vision. And our vision for at least transactional experience engineering is that we should provide a seamless and a hassle-free member experience while maintaining strong data, consistency guarantees, and ensuring resilient cross-service orchestration, and maintaining best-in-class performance. So consistency, resiliency, orchestration, and performance. So yeah, and we do I would say we follow the same general ideas like the rest of Vinted engineering. We want to keep it as simple as possible, as minimal as possible. And these, I would say, are 4 main reliability technologies that we use. So from bottom to the top, we have database, we have distributed logs, we have transactional outbox pattern, Kafka events and commands, and then we have pending state pattern and reconciliation jobs. This is one of the oldest tricks in the book. And we can start from the smallest common denominator. That's our database architecture. So in an ideal world, like if you have, like, let's say 1,000 requests per second, you can just have a single database, and you can have everything done in a database transaction and call it a day. But for our case, that's not so simple, because we need to horizontally scale, we need to scale vertically, we need to ensure that our databases do not exceed some specific size limits. If I remember correctly, we have around 400 tables, so it's still rather impractical to start them in a single database. So everything starts from a database. So this is our smallest common denominator that basically sets the standard how we want to proceed with reliability. And we try to keep our database shards closely matching the context boundaries from the previously showed context map, meaning that we are going to have conversations database, payments database, shipping database, etc. We have some constraints in place that we say that if your operation, like an HTTP request, does something, it can read from multiple shards, but it must write to exactly one shard, meaning not only vertical but horizontal as well. And we have a bunch of in-house tooling that notifies about cross-shard operations. So yeah, one of the drawbacks of the current database architecture, I would say, is that it's likely that we might get partial commits. Like, our databases are not perfectly isolated. So, but we have in-house tooling that allows us to identify illegal operations, and we try to fix them in a timely manner based on criticality. There is a nice blog about this in Vinted engineering website. You can read more from our SREs about it. And there is also one more thing. Like, it's no secret that we use MySQL, and the replication technology, I would say, is rather simple as well. So we always need to keep in mind that Vitess, and in turn MySQL, does not guarantee causal consistency. And what this means in simple terms, if you read from a replica some value, it doesn't mean that if you call the same method again, that the value will be there, because you might hit a different replica, and there is no way to guarantee that. So we always assume that there might be no data, and we need to be prepared for that. So moving up, we have locking solutions. So we use our own in-house, I would say, small framework for locks. We have a distributed ephemeral locking implementation. If you are familiar with Zookeeper, it kind of resembles that, but it's based on, well, again, MySQL. And basically, we try to ensure that all of our operations are idempotent, meaning that we can invoke them multiple times, and they will produce the same result every time, same side effects, actually. Yeah, and one of the drawbacks that we haven't met them yet, but hopefully we will never will, it's deadlocks. We try to minimize the locking scope. Like, if we have a huge operation, we need to ensure that the locking scope is very minimal. We try to fail fast in case something happens, in case we are unable to acquire the lock. And there's also the possibility, as I mentioned previously, of zombie locks. So because of our custom implementation, the lock is kept as long as the connection is open to the database, and that's gonna take some time. I'd say our average pod lifetime is 15 minutes. So in the absolute worst case scenario, we will keep the lock for 15 minutes. And then new rolling deployment will happen, and Kubernetes will restart the pod, thus dropping the connections. Moving on, this is a rather new topic, something that's new for us. It was introduced, I would say, like a year ago. That's asynchronous messaging. We try to reliably publish messages through Kafka. We try to refactor our monolith into less coupled packages and modules. And we chose to do we chose to do it using Kafka. So now when we approach, let's say, a big chunk of code and we want to refactor it, we first start by identifying the constraints. So because previously all of the operations were implemented with the assumption that everything will be available immediately, meaning that if you process a payment, then the user balance will be updated, the invoice will be scheduled for generation, and a bunch of other stuff will happen immediately at this exact moment, so after the request finishes. And we try to revisit those assumptions, and we try to find maybe there are some places where the results could appear eventually. For example, balance update. So if we know for a fact that the payment was successful, we don't necessarily need to show it immediately. We can wait on maybe 1 or maybe 2 seconds. The user will not be able to tell the difference because the balance is displayed on a separate screen. And we can decouple a big chunk of code, thus reducing the transaction block, the database transaction block. And in order to do that, there is one small thing. We cannot reliably publish a message. It's not possible because Kafka doesn't implement XA transactions, or how they are called. So in essence, it's impossible to ensure that your database commit and Kafka message produce would happen at the same time or not at all. So it's not atomic, meaning that in some cases you might get Kafka messages that are published if you use the publisher directly from the code. In other cases, you might get database transaction that's committed with the message that's unable to be published. So for that, we use a simple pattern that's called transactional outbox. And essentially, we still follow the least common denominator, that meaning database. So we always write all of our events first into the database, and then we have a background job that processes those events, reads them, and publishes them to Kafka. And yeah, so that's the last point that I missed. So we always try to write a single shard, and that shard should always contain an outbox table where we would store all of the messages that need to be published. So obviously, this is still a new thing. We are still working on the tooling together with the platform team and SRE team. We are working on replicating Kafka, ensuring reliability. So it's still an early thing, but we might see that Ruby might not be the best approach here because of the way Kafka scales. Because Ruby threads are actually non-existent, they're fake, like Pythons. So we are investigating some options, how we can do it better. Maybe scale using pods in Kubernetes, maybe do some kind of orchestration magic, so to basically allow the consumers to consume more messages faster. And currently, we are just using Ruby threads. It works for our use case, but as I mentioned, we want to scale. Yeah, Kafka is very static, so configuration must account for all possible peak load times. So we always calculate the amount of requests we expect. We always calculate the peak requests. And basically, we are forced to always scale Kafka topics to that amount. And another thing that I barely touched in the previous slide was legacy UI. There are places where the Vinted application was designed to expect everything to happen at the same time, immediately. So it's hard to refactor because you need to take member experience into account as well. You cannot just, make all of those things into something that's asynchronous. And this is one of the oldest tricks in the book. That's one of the first, I would say, transactional experience reliability patterns. It's pending state pattern. So it's the good old way. In essence, this could be replaced by Kafka if Kafka supported delayed message queues, but because there is no general way to support delayed messages, this is something that we are still using. So for example, whenever we want to call a service, instead of calling the service, we register a pending state object, lightweight object in the database. So we do, again, going back to the first slide, database is our atomicity constraint. So we always register something in the database with pending state, then we do the external system call, then we update the state. And then in the background, we have a batch job that scans for those pending objects and reconciles them. So in case something bad happened, and we were unable to call the external service or something failed, we are aware of the fact that we wanted to call it. And the batch job, in case we were unable to, for example, receive response from external service, the batch job will be responsible for pinging that service directly and checking the status of the operation. So whenever we create the lightweight object, not only we set the pending state, but we also set the identifier that we are then providing to the external service, like payments or Vinted Go. So yeah, so this also has some drawbacks. We experience bursting reconciliation. So in case we have an infrastructure hiccup, we might see that our reconciliation jobs pick up a bunch of items which are in the pending state. And then we effectively almost do a distributed denial of service attack to our external service providers, because we pick up all of those and then we query all of them, so we are not doing any throughput control. And the reconciliation doesn't happen in real time. Essentially, it happens, I would say, in 20 minutes or 15 minutes, so it affects the user experience. The user sees in the message thread a spinner, basically, or loading state message or something like that. So yeah, these are all of our technologies that we use. And this is a very, again, simplified flow of how it looks like to process a payment request. So we start by registering a pending debit in the horizontal shard in Vitess. We call external payment service. We then acquire the lock, and we update the status in case the external payment service says that everything is OK. We add a message to the outbox, commit the database transaction, release the lock, and that's it. In case something fails, we have a reconciliation job that queries those pending debits from the database, again acquires the same lock, gets the current status of that specific payment from external service, and does reconciliation logic. Either fails or succeeds, or it all depends on a bunch of business rules. And then we also have outbox job that reads all of those outbox messages that we just added. It selects them from Vitess, it publishes them to Kafka, and it deletes them. And this also has a nice benefit because we are now expanding our data centers into different regions. This also adds a nice benefit that we can use Kafka producer batching. So we are no longer impacted by latency between data centers as much. And once this completes, we have a consumer for, in this case, this is just an example for fraud tracking, and it consumes a message that a payment was just processed. It does a bunch of logic behind the scenes that's not important for us, and then it makes a decision whether the payment should be refunded and reverted or whether it can proceed. So yeah, this is pretty much it. This is how it looks like, and that's the end of my presentation.